Welcome to the last lecture in CS61C. We're done. This is it. This is the last topic we're going to cover in this long class. So let's start off by doing a recap of what you've learned this summer and how much you've learned. So far, you learned how software works, right? Then how C works as a level of programming language, how that becomes assembly language, and how that becomes zeros and ones. Then we learned how hardware works, how logic gates work, and how we can use them to build more complex pieces of hardware, and we could even build our CPUs themselves that could actually do work on the zeros and ones that we created. And then finally, we looked at how our computer could control software and hardware working in tandem and exploit different parts of it to give ourselves huge speed increases. And that's great. And you learned about it, and you realized it, and you practice it throughout these different assignments. And so we're going to end the class by asking one final question. What happens when the real world gets involved? When I'm talking about the real world, I mean what happens when there's mistakes or faults or failures in our computers. Things break in the real world. This is a fact. And so the theme of today's lecture is going to be how can we ensure that systems can function reliably in the face of failure, and how could we improve upon these systems to make sure that they're able to stand back up when they fall down. And so we can kind of unify these under three broad categories. Dependability. How dependable are our systems, right? Can you rely on them? Will they do good things? Redundancy, right? Storing multiple copies of our data because in case one gets lost or one gets corrupted, I have backups, right? And then lastly, error correcting. When our systems fail and an error occurs, how can I find and fix the problem? So you can see this is very relevant nowadays, where systems are more than just a computer. Think cloud computing facilities, or things that involve multiple pieces of hardware strung together at once. This is the most realistic kind of view and perspective of how computing works. And so this is going to be the last topic in the class. Okay, we're going to begin with dependability, which is going to define for us the terminology that we're going to use that will allow us to actually measure how dependable things are and how we could actually look at our systems and analyze them in terms of these errors and faults that they might have. So there isn't too much technical aspects to this, right? This is very straightforward, right? Dependability, the system is considered dependable if it's highly available or it has a low probability of failure, right? Or that there's an outage, right? So it's unlikely to encounter a failure, and even if it does fail, it's going to recover quickly and get back online, right? It is an available system, okay? One thing to keep in mind, though, is that, systems are actually quite complex nowadays. So just because one aspect of your system might be dependable, if it's connected to other aspects in the system, you're only as good as the least dependable aspect, right? So therefore, you need the dependability of all the components of your system to kind of view the overall dependability of your system. Okay, so we can kind of break up dependability into the few tasks that happen in between that kind of let us measure what's going right and what's going wrong, right? So usually these are like faults. When you're doing something, things are going great, right? Services are delivered as specified, things are accomplished, and then you might encounter some sort of failure. And we're going to keep failures very general right now. Right? Could be a hardware failure or a software failure. Just think maybe like a cluster goes down in a server room or something. Some failure might happen. Okay, so therefore we need to interrupt what we're doing, and we need to repair what we're doing, and then we need to recover and get back and pick back up where we left off. Right? It's kind of like in the same vein when we look at like exceptions in your code, except this time we're looking at it at a much larger scale in the real world. Think of a server room, in Iceland or something, right, that has thousands upon thousands of computers in it. If one computer's go down, right, you have to make sure that your whole system is dependable enough that way service will not get interrupted, really. Okay, so here are the terminology that we use to actually talk about dependability. The first way is how we measure reliability, okay, and this we define as the mean time to failure. How long does it take on average before our system fails? Up next, how do we actually measure how expensive a service interruption is? We're going to call this the mean time to repair. So after you fail, how long is it going to take for you to get back up online? And then we can define the mean time between failures as just the sum of these both. Right, once one failure begins, what's the mean time until the next failure begins? Well, it's, until the first failure finishes getting repaired, and the mean time until the next failure. So the sum of these both. And therefore, we could actually define availability overall as the mean time to failure divided by the mean time between failures. That is how available our systems are. Right? An overall goal that we're going to want to do is we obviously, to have a good and dependable system, want to improve the availability of our systems. So there's two ways of doing this, just by looking at the math here, right? We can increase the mean time to failure And we can do this by, having like, better hardware and software and having better fault tolerance, right? Having more reliability in that regard. And then we could also reduce the mean time to repair by having, better and higher quality diagnoses and repair systems for our machines that might go down, okay? So we can actually define this even further into something called the annualized failure rate, which lets us generalize it into a huge scheme, right? So the annualized failure rate is defined by this equation. And so for example, we'll just use this example of like disks as a system, okay? So we're going to take the rate that disks fail per hour, multiply by the number of hours per year, and then say how often does this happen for one disk. And so this is our equation just for the annualized failure rate. It's basically just figuring out, basically generalizing the mean time to failure over kind of the entire year. Okay, not too different of a measurement. Okay. Often, when we're looking at dependability and availability, 90% is kind of the low threshold. If you have a system that's available 90% of the time, you're kind of failing as a system. So we tend to measure availability in terms of like the number of nines available. So even having 90% is actually quite expensive. If you have 90% availability, that means that per year, you're going to need to spend at least a little over a month, 36 days, repairing your system. Kind of gross. Okay, if I have 99% availability, that's better, only 3.6 days. 99.9%, 526 minutes. Okay, right, so it gets further and further. And, near like some of the best is, 99.999% availability. We only get 5 minutes of repair per year, which is essentially nothing. Right, so we always want to be looking in terms of the number of nines that we have. So let's look at an example. So here's our disk system. So I have 1,000 disks, and they tell me that, every 100,000 hours or so, it fails. And when it fails, it takes 100 hours to repair them and get them back up online. So therefore, here we begin. It takes 100,000 hours, then we're going to fail. It's going to take a little 100 hours right here for us to get back online. And then we have another 100,000 hours before we fail again, right? And so our mean time between failures is right up here, right? Between when this failure starts and this failure starts is the sum of the mean time to repair plus the mean time to fail, okay? And so we could even see the availability here as well, right? We could just divide it here, right? The mean time to fail means that things are going well and I haven't failed yet, divided by the mean time between failures gives us, in this case, a 99.9% availability, which is not that bad, okay? So how could we actually get it better? Currently, we only have 3 nines, which is not bad. What if I want, 4 or something like that, right? So what we want to do is we want to get that ratio of mean time to failure to mean time between failures to be as close as possible to 1. Okay, and since we can't really change the mean time to failure in this regard, let's say, okay, for the sake of this example, I want to improve my mean time to repair. How can I improve my repairing scheme to give myself 4 nines? Okay, so, we can just do some simple algebra here, right? Here's our equation for availability, and I want 4 nines worth of availability, and so you could rearrange. Now, in this example, we're just going to say that, our mean time to failure is fixed. We can't really do anything about that, but I can change my mean time repair. So in this case, if I wish to have 4 nines of availability, I need to decrease my time to repair from 100 hours before all the way down to around 10 hours now. And that'll give me another kind of, improvement in my availability, which is honestly really worth it in my opinion. Okay, so that's it. That's actually all the terminology we need to look at dependability. We're basically looking, when does it fail? How long does it take to repair? All these kind of systems, right? In a big picture, right, how does this take place in the real world? Okay, in the real world nowadays, as we learned in like the last lecture with warehouse scale computing, a lot of systems and a lot of what you're doing on the cloud is really just a ton of computers living in some shed somewhere in the middle of nowhere, right? It's doing all of your work there, right? And so the dependability of those systems are arguably super, super important because they essentially run a lot of things that we use, right? Google Slides, Google Docs, a lot of websites, storage solutions, Piazza. I mean, like all software you can think of nowadays is getting run on the cloud. So you need to make sure that these are dependable. They don't go down, but when they do go down, it's going to be quick before they come back up, right? I think recently, a few weeks ago, as of when I'm recording this, Cloudflare, which is like a DNS service provider in a way for a majority of the internet, went down because one small DNS server, I think in Atlanta, Georgia, went down. And a good chunk of the internet went down. AWS went down, a lot of Google servers went down. It was just insane. But it was arguably a very dependable system because it had been a long time before anything like that went down. And within, I think, 1 or 2 hours, they were able to isolate exactly where the problem was and fix it and bring the whole network back up online. So there you go. Mean time to repair for them, quite short as well. Okay. But, it kind of speaks to a larger theme, right? It kind of has a nice dependability has a corollary to Amdahl's law, right? Amdahl's law said we can only speed up our things as fast as like the portion that's even able to be sped up. So in a way, when we think about dependability with these complex systems, if you want good dependability, you need to make sure that you're actually able to have all components of your entire system to be as dependable as possible. And a lot of companies put a lot of money into their architecture of their kind of, compute to make sure that you have as much dependability as possible. So in 2013, for example, Google released their numbers, and I think this is like 7 years ago at this point, right? Back then, when Google Cloud was like pretty big, but definitely nowhere near as big as it was today, they had 99 point like around 9% availability. They had three nines. That's pretty good. Think about how much Google runs in the world, and they were to make this guarantee. And to think that in the 7 years since then, Google has scaled up their cloud compute, AWS has scaled up their cloud compute, Microsoft Azure has scaled up their cloud compute, all of them have scaled up their cloud compute, and they obviously want to be getting as many of these nines as possible. And they will put a ton of money into the architecture and dependability and the redundancy and error correcting that we're going to go over today to make sure that you are able to utilize all of their applications and basically surf the web and do anything you want with little to no problems whatsoever. So that's it for about dependability. Let's kind of finish this off with a question. Okay. There's a hardware glitch in your system that makes the mean time to failure decrease. Okay, so the time that it takes between failures is getting smaller. All the following statements true or false. Our system's availability will increase, or, and I guess, our system's annualized failure rate will increase. Okay, well, let's look at each one. So, let's look at the first one. Our system's availability will increase. Okay, well, remember the definition of availability is time to failure over time between failures. So as time to failure shrinks, the fraction is going to get outweighed by the fact that the time to repair do not get any better. Okay, so therefore this is false. The availability will decrease because now I have less time between each failure, right? And I still have a long time to repair as well. So my availability is still going to go down as well. Not so good. Okay, what about annualized failure rate? Okay, well, the mean time to failure is defined as the average time until something goes wrong, right? So if this goes down, right, that means that you're going to have more failures happening per year, right? Because the mean time is decreased, so you're going to fail more often. So over the course of the year, your annualized failure rate is going to increase. Okay, so hopefully this is straightforward enough. This is just basic, straightforward terminology. That way we have a way of formalizing mathematically how we can analyze how well our systems are running in terms of failure rates and how well they're doing on actually, getting back up when they fall.